Okay, so as promised, I'm going to do this example from the book again, but I'm going to do it using different loops, and I'm going to choose my currents differently. So here's the same circuit with the 80 volt and the 45 volt batteries. I'm going to choose my current I1 to be in this direction. I'm going to say let that split off into I2 and I3. And if you pay attention, you'll see that the direction of I3 is actually different from the direction that it was the way the book drew it. So at this junction point right here, I know that I1 going in is equal to I2 plus I3 coming out of that point. And I'm going to pick two loops around the circuit, and they're going to be not the same loops that I picked before on purpose to show you that it really, really doesn't matter what loops you choose, and to also show you how to deal with the possibility that sometimes your arrows will be pointing in the wrong direction. So let's pick, I don't remember where I think last time we started here and here. So let's start here in this top corner, and let's go all the way around the outside loop, not the inner loop, but all the way around the outside and come back to that point right there. And let's go this way. So what we see is when we start, we're following current I2, and we go across a 30 ohm resistor, so there's a voltage drop of minus I2 times 30 ohms. Then we reach this point here. There's nothing until we get to this 20 ohm resistor. Notice now we're in the part of the circuit that's labeled I1. And we are going in the, well, no, wait, is that true? No, I1 is actually going in the right direction. So I1 goes around like this, from here to here. I2 goes around like this, from here to here. I3 goes that way. So we're going in the correct direction. So there's going to be a voltage drop of minus I1 times this 20 ohm resistor. And I1 is going in this direction. Then we go across a 1 ohm resistor in the region of the diagram that's labeled with current 1. So that's minus I1 times 1 ohm. And then we go through a battery, but we're going the wrong direction. We're going against the potential difference of the battery. So this isn't going to be plus 80 volts, this is going to be minus 80 volts because we're going from the positive to the negative terminal of the battery. Then we get up to here, nothing happens here. We're going to go to the resistor and we get back to where we started, so we know the total potential difference around that loop has got to be equal to 0. Let's simplify this now. We can rewrite this as 30 I2 plus 21 I1 plus 80 volts equals 0. Take a negative sign all the way through that and group together like terms and toss the units. Again, it's good physics practice to always keep the units with your numbers, but these things get really unpleasant looking if you leave those omegas in there. Now let's pick a different loop, and let's pick a different direction. Let's start here in this corner, and let's go around this loop this way. Okay, so we're going in the opposite direction of I2, but with I3. So what do we encounter if we start here and go this way across the loop? We encounter a 30 ohm resistor, but we're going the opposite direction of the current. So what we've got essentially is minus I2. Well, you can write this any way you want. I would write it like this, even though it's easy to screw up the signs. There's a potential drop minus, but the current is negative I2. So you're going upstream, so you're going to higher potentials. Minus is a positive. You come here, you're going through I2, then you split up to the I3 portion. You're going in the right direction of I3, so it's going to be a potential drop of I3 times 40 ohms. Then you're going across the minus potential drop across this 1 ohm resistor, so that's minus I3 times 1 ohm. Then you're going again upstream from the battery, from positive to negative, so that's going to be minus 45 volts, not plus 45 volts. You get back to this part of the thing, and you're back home again. So you know the total potential difference around your loop is equal to 0. If we toss the units and put, so minus minus is plus, so that's 30I2 minus 41I3 equals 45. Okay? If I didn't screw up any signs there, and again, it's so easy to screw up signs in these problems. So there's one equation. There's two equations. There's a third equation. Three equations, three unknowns. I should be able to solve that simultaneously. I'm going to be super lazy though, and instead of doing that algebraically, we'll just go to Wolfram Alpha. We'll make Wolfram Alpha do our hard work for us. We'll call I1 X and I2 Y and I3 Z just to make it easier for us to type the solution. So our first equation is I1 equals I2 plus I3. So that's X equals Y plus Z. Our next is 30I2. So that's 30Y plus 21X plus 80 equals 0. And our third equation is 30I2 minus 41I3 equals 45. So that's 30Y minus 41Z equals 45. And if I didn't make any sign mistakes, this should solve for x, y, and z for me. For some reason, Wolfram Alpha solves, it gives you the answer in fractional form. We'll have it divide through that and ask for the approximate form. And what does it tell us? It tells us that x, which is our I1, is equal to negative 2.58. Our y, which is I2, is equal to negative 0.858 or 86, and our I3, which is z, is approximately equal to negative 1.7255. And those should all be in amps. If we come back here to our solutions, this is the answer we get from Wolfram Alpha, okay, for this system of simultaneous equations. And again, I know you guys all know how to solve systems of simultaneous equations. You know that I know how to solve systems of simultaneous equations, but rather than stumble through that process and risk making mistakes, we will just let Wolfram Alpha do that for us and save us some time. What does that mean as far as our little circuit here? The way that we drew the directions of the current, I1, I2, and I3, we drew I1 this way, and we got a negative answer. So that tells me that I1 is 2.58 amps that away. That I2 we drew this way, and we got a negative sign, which means I2 is 0.86 amps that away. And I3, which we drew this way, is actually this way, 1.7 amps that way. And if you take a look at those signs, and you take a look at the answers that your textbook got for I1, I2, and I3 based on the conventions that they used for the currents, their I1 was this, and they got negative 0.87 amps, which means 0.86 amps that way. Their I2 was this, and they got the same answer we did. These are the example answers that I jotted for myself, so I wouldn't have to go look them up again. And their I3 was the way they drew it in their original this way, and they got 1.7 amps, which is exactly what we got. So choosing different directions for the current, choosing different labels for what happens at the junction, and going around the circuit in different loops, we still get the exact same answers. The signs are different because we chose different directions for our initial currents. That is okay. And so you don't have to bother yourself too much by trying to figure out before you solve the problem, which direction the currents are going. You just draw those arrows any old place you want, but you do have to be careful when going around the loops that you are making clear whether you're going with the current, in which case it's a voltage drop of minus IR, or if you're going against the current, you're actually going upstream to higher voltage, and it's minus IR, or plus IR for that voltage difference as you go around the circuit. I might do one more example of this and try to find a simpler example, one with maybe just one battery and one or two resistors per loop, just so that we see a bunch of examples of this, because it does take practice, and then, like I said, there's a lot of room for error. But we'll do a few more of these, and then we'll move right on to alternating circuits and things a little bit more straightforward and a little less complicated. So I'll go ahead and stop it there. And yeah, we'll be done for our Thursday videos, and then we'll move on to something different.